Kyle Kovanoff at Columbia University gave an answer to this question. He wrote the answer down in some symbolic notation, which it would take some time to even explain what the notation means, but it's a notation for symbols involving annihilation and creation operators. But he wrote it down sort of as if it had just come out of his brain and some divine inspiration. It seemed very mysterious to me. If I was very persistent, I could have read his paper, and his paper does explain how he got the idea, but it still seemed complicated to me. Still would have seemed complicated to me if I'd read it carefully. I still wouldn't have understood it really. But in 2012, Jeffrey Morton and Jamie Vickery showed that actually you can understand these things in very simple terms using finite sets and a bit of category theory. Let's see. Okay, so the idea is, as I said, that the creation operator is a process that creates a new particle of some type. The annihilation operator is actually a little subtler. See, if I imagine creating a unicorn out of thin air, there's basically one way for me to do that, if I could do it. Poof, there's a unicorn. But if you're in a room full of unicorns, and then you're talking about annihilating a unicorn, that's a more subtle issue, because you have to pick which unicorn you're going to annihilate. Not that it's a situation that comes up very often with unicorns. Yeah, except when there are no unicorns. Then there's a unique way. So that's actually what gives rise to these commutation relations. So here what I'm doing is I'm eliminating the subscripts that I'd written before in Heisenberg's relation. I'm just thinking about one type of particle. So what this equation is really saying is that there's one more way to create a particle and then annihilate one than there is to annihilate one and then create one. So the idea is that if I, for example, put a piece of chalk into a box that may already have some chalk in it, and then take one out, there are lots of pieces of chalk to pick out, and there's one more, because I just put one in, one more way to do that than if I had first taken one out and then put one in. So I'm imagining that the pieces in the box really exist, and the one I'm putting in, it's just sort of coming out of nowhere. So I don't imagine like I'm taking it from some other box or something like that. So this is actually the combinatorial significance of Heisenberg's commutation relations. I became very excited when I learned this, which really, I guess I learned it from thinking about André Joyal's work on species and combinatorics, because I had always been told that this is like some unfathomably deep concept from quantum mechanics that's sort of mysterious, that things don't commute. But in fact, it's really not so mysterious. It's really just a matter of this fact about balls in boxes, or unicorns, or whatever.
You need Virgin Girls for that.
To do what?
To see a unicorn.
To create
Only Virgin Girls are able to see unicorns.
Oh yes, that's true. Yes, that's right. Yes. Yeah, so I guess I'm not suitable for that example. Yeah, that's right. Unfortunately, that tapestry is not available for public view now. My wife and I went to the Cluny Museum, where they have the Virgin and the Unicorn, and they advertise for you to go in there. You go in there, it's the very last thing you see in the museum. You go on and on and on. At the very end, there's a guard sitting there, and he says, "Oh, I'm sorry, the painting is not available to be seen now." And we said, "Oh, well, it's okay. And he said, no, it's not okay. The people at the front desk, they don't tell you. And everyone comes to me and they ask me. And then they all blame me. So his job is to like deliver the bad news.
Mr. Abbas,
Yes.
in this picture you have this equation. In this equation there is a correction plus 1,
Right.
and before you have another correction plus delta Ig.
Yeah.
And this correction is, we are really in non-commutative things.
That's right.
It's a good thing because it's another point of view that quantum mechanics, it is the non-commutative which is really involved,
Right.
mathematically speaking.
That's right. So, but I'm trying to say that the non-commutativity in this relation in quantum mechanics is not something mysterious. It's something that you can
Yes.
study macroscopically. So just like putting on your socks and shoes is a non-commutative operation, which nobody claims is quantum mechanical. I think this is quantum mechanical, but I think that there's a way to understand it where you don't, where you just think about combinatorics. Yes?
Can you justify the fact that when you illustrate this by saying there is one more way when you have a box with one particle in it, but
Well, with any number of particles already in it.
there is a difference with any number of particles, but why one? With one it works, with 2 or 0 it doesn't work.
No, I didn't say that
one
you...
at the start, I mean.
No. This box could have any number of pieces of chalk in it, and then I create one. I put an extra piece of chalk in, and now there are 12 ways to take one out.
Okay, and then plus 1. Okay,
But if I
go ahead.
first took one out and then stuck it in, there would only be 11 ways to choose the chalk because I hadn't put the extra one in yet. So it doesn't depend on the number of particles that are already there. So it's a general effect. Yeah. So the 1 is just a general rule. So the question is, how can you make this idea mathematically precise? And so a nice way to do it, which goes back to André Gérial, is to model this bunch of pieces of chalk as a finite set. And so think about the groupoid of finite sets. So I'll call S the groupoid of finite sets. So an object is a finite set, a morphism is a bijection between finite sets.
So it's an isomorphism.
Right. Yeah, so because it's a groupoid, all the morphisms are isomorphisms. Yeah, so I'm not looking at general functions, just bijections. So there's a functor called +1 from the groupoid from S to itself, which takes any finite set to its disjoint union with a particular one-element set. So we pick a one-element set and call it 1. There's this functor here. So that's a way to think about the creation operator. It adds one element to a finite set, which we could call the elements particles if we wanted to act like physicists. That's the application. But what about the annihilation? There's not a functor from the groupoid of finite sets to itself that takes a finite set and removes a particle. A functor has to be a systematic method. There's no systematic method to pick one out of n elements. There's no best way to choose one. Luckily, we don't really want to choose one for our application. We want to take all possible ways. That's what we need. So we need to describe this sort of non-deterministic process that picks any one out. And we can describe that using spans of groupoids.